Okay, yeah, so it's a great pleasure to have everyone here for the Distinguished Icon Seminar today. Just to give a very brief overview of Icon for those who are new to the center. This is a center that officially launched last year. It's a Center for Innovation and Control, Optimization, and Networks here at Purdue. And we have the benefit of having a large number of faculty working in these important areas. Spread out over the entire campus. So across the College of Engineering, across mathematics, computer science, Purdue Polytechnic. And so the goal of the center is really to provide an organizational structure, a home for bringing together all these people, these researchers working on important problems, so that we can coordinate our efforts and provide solutions to grand challenges. And as part of this, we have a Distinguished Icon Seminar Series, which brings to campus, at least in virtual form this year, some of the luminaries in the field who've really made seminal contributions to control theory. And today we have Professor Brian Anderson, who's going to be talking to us about social networks in the spirit of the interdisciplinary nature of this field. So I'll turn it over to Xiao Shui to introduce Professor Anderson.
Good afternoon, everyone. My name is Xiao Shui. I'm a faculty at Purdue AE and also co-direct the Center for Icon with Shreyas. And Shreyas mentioned, this is a new center. And during our center launching events, we will organize a series of distinguished seminars from our distinguished speakers. And today we have a very special and a distinguished guest, Professor Brian Anderson. And he is a pioneer in many research fields, especially in optimal control, adaptive control. And he is also a great mentor and with many excellent students graduate. And actually, I have benefited a lot from collaboration with him since 2008. So in the following 2 minutes, I will introduce Professor Brian Anderson. So Brian was born in Sydney, and he took his undergraduate degree in Sydney University, and then a doctoral degree at Stanford. And he became a professor at University of Newcastle in Australia from 1967, and also become the department head, I believe, at the age of 26, right? And then Brian moved to the Australian National University and also took the position as the professor, department head, and later on the dean for the School of Information Science and Engineering. And he retired from the ANU as a distinguished professor and was appointed emeritus professor in July 2016. And then he became a distinguished professor at Hangzhou Dianzi University. Brian's research has been internationally recognized by many awards. To name a few, he's the recipient of the IEEE Control System Society Body Prize and also the IEEE Control System Award and the AFAC Qualzar Medal and the IEEE James Mulligan John Junior Education Medal. And Brian is a foreign member of National Academy of Engineers in the United States and was the president of the AFAC. And he served as the president of the Australian Academy of Science for 4 years. So Brian, welcome. And now it's all yours.
Thank you very much, Xiao Shui. Would you wave your hand if you can hear me?
Yes, yes.
Good.
I will stop sharing and
yes. And are you seeing the screen sharing satisfactorily?
Yes.
Wave your hand if you can.
Yes, yes.
Thank you. Well, I'm talking about something that doesn't have apparently much to do with aeronautical engineering, but I will explain a little bit of connection in the course of the seminar. But to begin with, I want to thank Xiao Shui Mo very much for the invitation. There's a personal connection as well as a technical connection, you might say. And I've had a principal colleague on this work who was formerly my PhD student, and that's Ben Ye, who's now in Curtin University in Australia, and I want to thank him. There are two key overview references for what I'm talking about. And one is a book, which Ben Ye wrote, and the other is a survey paper, which the two of us wrote and was published about 18 months ago. There were a number of other key collaborators on our work, and here's the rogues gallery of those people. So if there's an overarching goal for the seminar, it's this. It is to illustrate how dynamic models, that means differential equations or difference equations, can be used to capture the evolution of opinions of a group of people who are exchanging ideas and thereby exerting influence on one another. And what I'm going to do in the first part of the seminar is review standard ideas of social networks and opinion dynamics. And then I'm going to talk about three developments of these ideas, which came from Ben and myself. So what is a social network? It's a group of people, or maybe a group of organizations, who are interacting using social relationships. So one good example is Facebook, and that involves a very large number of people. And of course, there are small networks too. A tenure committee at a university, a government cabinet, a jury panel in a criminal trial, or a board of directors. These are all examples of social networks where people are discussing things and often coming to a collective opinion. So what's roughly going on in this process is the following. Each individual has an opinion value, which is, if you like, a real number on an issue or topic, and they share their opinion value and discuss why they've got it with other people. For example, in relation to the question, self-driving cars will soon replace human-operated cars, or maybe they won't. Some people start off with the view of one, which is they're certain, and other people start off with the view of -1, there's certain self-driving cars will not soon replace human-operated cars. And after a discussion, the group comes to some sort of consensus where the balance of opinion is in favour of the proposition, but not giving you a certainty. So that corresponds to the level of about 0.45 in the opinion level. Now, the social network problem for engineers that this throws up is really, how can one systematically model the interactions between the agents that would reflect this behaviour? So if you go back in the psychology and sociology literature, you'll find many examples of models to deal with opinion dynamics, and some are actually dynamic models that discuss how people change their views. And one of the oldest of these is associated with three names. And if you can read the fine print, it's really, these are 60 years ago, this model. There are continuous time models too, and they have various names. But the one point I want to draw from this slide is that some of these continuous time models are virtually the same as a model that's been used for studying the convergence of robots to more or less a single point or airborne formation control. R3 says mathematical models of the distribution of attitudes under controversy. That's social networks. R4 says consensus seeking in multi-agent systems under dynamically changing interaction topologies. That's multi-agent systems. And the mathematics in these is just about the same. So some high-level issues. We might say what we're trying to do is develop mathematical models for describing opinion dynamics, and they need to reflect the observations of sociologists and psychologists. And maybe our models could predict some phenomena. We might be motivated because we're running a company and we want to make sure that our employees are happy or our customers are responding favorably to our latest marketing initiatives. And if you were to look at a very detailed, this has happened to me before where I lose the, an example of something we might be particularly concerned about is this. We mainly tend to interact with people whose opinions are similar to our own. Can you capture that aspect in a model, and what phenomena is thrown up when that occurs? So now I want to tell you what the de Groot model is, and this is this thing that goes back about 70 years. We're considering a single topic of discussion, and it's among n individuals. And the opinion of individual I is updated at each discrete instant of time. And that's the update equation. And you will see that actually individual I's new opinion is a linear convex combination of his or her prior opinion and of the neighbour's opinions, because the Wij's sum up to 1 and they're all non-negative, and that gives you the linear convex combination property. Now I want to make a very important point here. The linearity here is not a consequence of the equation capturing some physics law like Ohm's law or Maxwell's equations or Newton's law. The linearity is an assumption the original writers of this material made because they thought it would be easier to think about opinion dynamics that way. So the basis of the linearity is much more fragile than it is, say, for linearity where you're talking about vehicles moving around the sky. We can represent those equations if there were, say, 3 individuals talking and use a matrix, and this is the sort of picture we'd get. And we can associate a graph with that matrix, and you'll see there's no arrow from 2 to 3, and that corresponds to the fact that there is no dependence. I'm sorry, let me say again. There's no arrow from 1 to 2, and that corresponds to the appearance of this 0 here. So Y2 does not depend on Y1, and that's represented in the graph by the absence of an arrow here. So W is a row stochastic matrix, and if you were to plot the evolution of the opinions at each discrete instant of time, if they start off all different, here the opinions all come into consensus, which is a common phenomenon, of course, with many committees. And if you ask for the mathematical explanation that's inherent in that modeling, the connectivity of the graph and the row stochastic property of the matrix is what produces consensus. There is a continuous time version of the de Groot model, and it involves a Laplacian matrix instead of a stochastic matrix. And the variables can be taken not as opinions, but as points in a Euclidean space, and their derivatives are the agent velocities. And consensus means point agents converge to a common point. And that reference I gave you earlier is dealing with this sort of issue. So you'll have seen that I showed you a graph in that picture, and they are a convenient way to represent a social network. And the social network people probably call them influence networks. And the graph has got a set of vertices. It's got a set of edges which are ordered, and they represent directions of interpersonal influence. So there's an arrow from 3 to 1, meaning that individual 3 is influencing the opinion of individual 1. W is the matrix that captures the strength of those influences, and connectivity, the word I used before, means exactly what you would think it means. I won't bother defining it. And what I've been saying is that with the de Groot model, topology conditions on the graph and structural conditions on the influence matrix give you the social phenomenon of consensus. So what I'm going to do in this talk is explore 3 recent developments of social network modeling, and they all build substantially on this group model. And the first deals with differences in private and expressed opinions. Now, what does that mean? In many situations, when we are sitting in a group, we may hold a private view and express something just a little bit different because we feel in some way pressured by the other members of the group. For example, if I'm in a company and I'm a junior and my boss is sitting at the table with a few other people and myself and says something which I think is really wrong, I may express even mild support for my boss's view, and I probably wouldn't say, well, I think you're making a huge mistake, because I feel pressured by the committee situation and my relationship with the boss. So the broad question I want to consider is, how does the pressure from other group members affect the process of opinion dynamics? So there's quite a lot of literature on this that is principally qualitative and consists of laboratory studies and field studies. And it's been found that group pressure, this is not unexpected, and it's more or less what I've said, can modify and distort an individual's judgment, even in the face, though, of overwhelming facts. And individuals can go on to knowingly express a highly altered form of their private opinion. There's also a phenomenon called pluralistic ignorance. So let me give you an example of it. Suppose a lecturer gives a very, very poor lecture and at the end says, are there any questions? And no one says anything. And I'm there and I don't say anything because I think there are no questions because everybody else understood it. And my friend doesn't ask a question because he hears nothing and so thinks everybody else understood it. And so most of the people in the room think that the lecture was readily understandable, when privately most of them think it was a bad lecture. That's an example of pluralistic ignorance. In a factory, it's well documented that if you've got a group of people with different productivity rates, the people with high productivity rates in some way get pressured to lower their rates to match a group standard. And this stuff, field studies and laboratory studies, goes back really up to 70 years. So if we want to put opinion dynamics into this, the notion is roughly this, that individual I expresses his or her opinion and obtains the expressed opinions of other people, and then individual I updates their private opinion, taking into account their previous private opinion and the expressed opinions of others, and then individual I determines what his or her new expressed opinion should be, and it's the private opinion but altered by the group pressure effects. So I want to show you how you can build a model that is consistent with these ideas, and it incorporates two notions of behavior which we understand. One is stubbornness, and the other is the ability to withstand pressure from other people or resilience. Now, it turns out that stubbornness has been considered in opinion dynamics for some time, excuse me, maybe 30 years or so. And the particular model is called the Friedkin-Johnson model. And if you look at that equation, it's got the WII and the WIJ of the de Groot equation, but it's got another term or another parameter as well, namely lambda I. And this lambda I is associated with the stubbornness. And if lambda I were 1, then this equation would be exactly the same as the de Groot equation. If lambda I is 0, it's telling you that the ith individual's opinion is always going to be stuck at their initial opinion, and they will never change in the light of the expressed opinions of the other people. So lambda I is normally somewhere between 0 and 1. A very stubborn individual would have lambda I very close to 0, and an individual that had no stubbornness at all or very low stubbornness would have lambda I very close to 1. And the stubbornness term does create disagreement and an absence of consensus. So that's been known for some time. So if we want to bring in the difference between expressed and private opinions, we can write down that equation where the inputs to individualized decision process are now the expressed opinions of the other individuals. And otherwise, it's the same as the Friedkin-Johnson model. And then the individual also produces an expressed opinion that's a combination of their private opinion and the average public opinion present across the whole group. And phi I is what we call a resilience parameter, because if phi I was 1, the expressed opinion would be the same as the private opinion. If phi I is 0, the expressed opinion would be simply the public opinion. In that case, with phi I 0, the individual has no resilience. They completely go with the flow. If phi I, on the other hand, is 1, then the individual is fully resilient and doesn't take any notice of what other people are saying and simply says what they truly believe. So you can put together a linear model. It's just a higher dimension version of what's come before. And under reasonable assumptions of connectivity and opinion values in the interval 0, 1, then you get convergence to a steady state. And the convergence itself isn't difficult. And what's interesting to study, though, is the final opinion distributions. So the social interpretations, first of all, and the mathematical ones are down the bottom of the slide, the private opinions in the steady state, Y star, are a convex combination of the initial private opinions. And the public opinions or the expressed opinions in the steady state are a convex combination of the private opinions. And you get this with R and S being invertible positive row stochastic matrices. You can prove that. So the stuff down the bottom is what you prove, and the stuff up the top is the way to interpret it. But it's useful to think of it in graphical terms. By the way, there's no dependence at all on the initial publicly expressed opinions. The final state that you come to is given, of course, by the parameters of the system, but the private opinion initial vector and not ever the public one. So there's a persistent disagreement between the expressed and the private opinions. And here's the sort of picture you could get. The orange curves are the group of expressed opinions, and the blue curves are the group for the same individuals of their private opinions. And you can see that, first of all, the private and expressed opinions in the same individuals are different. I haven't said which curve is which individual, but it's plain that no orange curve overlays any blue curve. You can also see that there is a much larger disagreement among the private opinions than the expressed opinions. The private are blue, the expressed are orange. And you can see that the expressed opinions are enclosed or within the private opinions. So there is a kind of contraction of the spread of views in going from private to public or expressed opinions. And that can be quite important if you're asking your employees, say, whether they're happy and they give you public opinions, because what we have is an inequality. The expressed opinion spread, or what you'll get if you ask people, is less than the private opinion spread. And here's an inequality that tells you how much less it is. The private opinion spread is over on the right. And so again, there's a warning that public expression of opinions may not tell you how much disharmony is actually existing in a group. So there's a very famous experiment that took place 70 odd years ago, and really no focus on dynamics, but one of the things we did with this model was look at the experiment. So I want to tell you about the experiment and how it fits with the model. There are 8 people in a room and they're having a discussion, and they're asked which of the lines A, B, and C has the same length as the line on the left. So, of course, you can see that the answer is C. But the person running the experiment has told the blue people secretly before the meeting, when you're asked this question, you should say B, because I'm really interested in seeing how individual A reacts. So they're all sitting in the room, and the red guy doesn't know anything about this prior arrangement, and the red guy just hears the 7 of the 8 people all saying, oh, the line on the left corresponds to the line B on the right. So, of course, you can do this with many people and many experiments, and there are several possibilities that arise. The red individual may remain of the view and state that C is the correct answer. So he or she is then in opposition to the 7 blue individuals. Or the individual may say in the meeting that, oh, well, I think probably B, you're right, B is the answer. But afterwards, in a post-interview, says, well, I knew it was C all the time, but I just didn't feel like comfortable about saying so. Or the individual is so moved by the discussion that even after the interview, they still claim that B was the true length of the line. So you can model this with that model and adjust the parameters in a logical fashion to so to speak, correspond to high resilience and low resilience individuals, for example. And you'll get all 3 behaviours depending on the setting of the parameters. And here's an example where the individual retains more or less their private view, but states a public view or expresses a view that's consistent with B. So the blue corresponds to the view expressed by the blue agents. The dotted red corresponds to the expressed view of the red person, and the solid red corresponds to the private view of the red person as determined by discussion in a post interview. So the model that I've given you can also be used to demonstrate the occurrence of pluralistic ignorance, large and small network effects, and a wonderful example consistent with the collection of alcohol consumption data over a whole year for men and women in Princeton University. So it's a model that was consistent with laboratory and field data from the past. So to sum up then, I've given you a model and I've given you analytical results with relations between expressed and private beliefs. And the model was verified or validated, if you like, with these famous experiments. And it also, though, the same model displays or will give you pluralistic ignorance. So there's a lot more that we could do, including the detailed study of zealots and even bots in a large group, and take into account things like rate of change and so on. Okay, so now I'm going to switch to the second topic we looked at, which concerns the evolution of individual social power. And individual social power deals with the ability of an individual to carry the meeting or to have a significant influence on the outcome of the meeting. So there's yet another model, and it's called the de Groot-Friedkin model, which studies the evolution of an individual's social power, which is pretty much the same as their self-confidence, as a network discusses opinions on a sequence of topics. So what's going on here? Well, if we discuss an item and I have less influence on the outcome than what I thought I would, I'm probably going to be less and less confident of my own opinion. So when we go on to discuss the next item, and maybe I say something and people jump on me, so I have even less influence on the outcome from the second item than the first, and so I become less and less confident of my own opinion. So one's self-confidence and ability to influence an outcome can change. And the specific problem is, how does an individual's social power evolve when the interpersonal relationships are changing? For example, if there's a dynamic network topology or something like that. I should say de Groot-Friedkin looked at matters where everything was constant, except a sequence of topics was discussed. So let me give you an overview of the model. We're considering discussion on a sequence of topics, and first one might be, are Toyota cars reliable? And we reach a consensus on that. And then each individual, you or me, evaluate their influence on the discussion and update their self-confidence. Later I'll say something about how you update, but they update their self-confidence for the next topic. And then we use the new self-confidence to update the influence weights that they give to their neighbours in discussing the next topic. And then when they discuss the next topic, and the next topic might be, is a dog man's best friend? And so we go through that loop again, and then we go on to the next topic, which might be, let me see, is chess a sport? And so on. So how can we capture the change of self-confidence? First of all, we need to understand the effect of other individuals on a given individual. And we use a thing called a relative interaction matrix for that. And I think I've got a picture of one here. So this is saying we're not going to take any account of one's self-confidence in this picture. It's a relative interaction matrix that tells us how other individuals are influencing us. And one is influenced by 3 and not at all by 2. So the sum of the influences affecting 1 adds up to 1. Individual 3 is influenced by 1 to the extent of 0.3 and from 2 to the extent of 0.7. So that adds up to 1. And C is a row stochastic matrix, and it's technically what's called irreducible. And you should think of it as the relative friendship or trust that individual I allocates to all of its or his or her neighbours. Now, zeros are on the main diagonal, since for the purposes of this matrix, we're only considering other individuals. So as a row stochastic irreducible matrix, it has what's called a left parent Frobenius eigenvalue, which is positive, and the entries all sum to 1. So there's a quantity gamma associated with it. So individual I's opinion for topic S is updated according to the de Groot model, where this is the self-confidence that they're bringing to the discussion of topic S. And throughout the discussion of topic S, that is, as T varies, this is constant. And you go right through the topic, and then you update the time scale S. So T appears only during each opinion dynamics process, and S appears in here in that it parametrizes these things. And then there's an updating of social power, an updating of this thing here. And I haven't said yet how you update it. So we'll assume that timescales are decoupled, and we're interested in working in the S timescale. And this is a measure of self-confidence, and we'll just call it X, I of S. So as this evolves, in order to maintain the stochastic nature of W, we need to adjust these. And this is the way we adjust them. So if we increase this, we decrease all of these, but we keep the relative interaction matrix the same, or the relative weighting. So this thing just scales the C matrix to give us this Wij thing here. And the W matrix, it turns out, is row stochastic and irreducible if C has this property too. And that guarantees that consensus is achieved for each topic S. Now, how do I set the self-confidence at time S plus 1 for talk S plus 1? It's equal to individualized contribution to the final consensus value for topic S. And that's, I'm not going to show you how to compute it, but let me say it is easy to compute. So the contribution to the final consensus value is kind of how important or how unimportant a contribution is. So with that updating of self-confidence and running through topic after topic, the vector of X's updates, and there's a nonlinear equation that governs the update. And the detail isn't that important. It's important to see that it is nonlinear and kind of nasty. And the gamma I come from the Perron-Frobenius eigenvalue of C. But don't worry at all about the detail of the equation. It's just a nonlinear equation, definitely not a linear equation. So what's the outcome of running that equation? And the first thing to look at is a strongly connected star graph. So here, individual one in the center, so to speak, is discussing with each of the individuals. So he or she in the center is doing individual consultations, but there's no general committee discussion. And that's why we call it a star graph. And you can start off with any self-confidences that you like, but asymptotically, the center guy gets all the self-confidence and the other nodes get zero self-confidence. It's not exponentially fast, it's at 1 over S. And what you've got is autocracy. That is a dictator in the center. They're the only setter of opinions. No attention is given to the other opinions at all. So you could have this center guy saying, well, I've consulted with everybody. And if the consulting has all just been on an individual basis rather than the committee structure, it's in a sense kind of false as a claim of good discussion, because according to this model anyway, you'd get autocracy. So I'm sorry, I've skipped a slide here and I don't think I can recover it. For a non-star network, you don't get autocracy, fortunately. And the work that we did showed that this convergence is exponentially fast. The proof of convergence came along to the proof of convergence I'm referring to up here came a long time after the initial formulation of the model, because this was a nonlinear equation to work with. So, but a proof was given in whenever it was. We don't have the year here, but it's a fairly recent year. And with Ben and myself showed that was exponentially fast, which sounds like it's an academic exercise and only an academic exercise. But once you get exponential convergence, there becomes the possibility of handling time-varying problems and proving things about them. And you can envisage a situation where the topology can change over a sequence of topics. For example, if we're discussing in topic 1 something that's to do with economics, and in topic 2 something that's to do with the environment, then for the environment I might trust 3 because he's an environment expert, and for economics I might trust 2 because he's an an economics expert. And so the C matrix could change according to the nature of the topic. And in a government cabinet, for example, you probably have periodic discussions that cover social security and economics and defence and health and so on. So you can also get changes due to the joining of a group by individuals and the leaving of a group by individuals, which is maybe quite slow. And so we need to think about equations where the F matrix, which depends on, or the F mapping, which depends on the C, actually changes. And the result we can show is that initial conditions are forgotten exponentially fast, as long as you don't have a star graph. And the convergence of the XS sequence occurs to a unique trajectory that's nothing to do with the initial values, and the trajectory is constant if C is constant, and it's periodic if C is periodic. So sequential opinion discussion that's genuine and not just in a star graph removes the individual's social power or self-confidence exponentially fast. And what you end up with is just dependent on the sequence of topology structures. And to illustrate it, the dotted and the solid blue curve start off at different initial conditions, but merge. The dotted and the solid black curve start off at different initial conditions and merge. So there's changes of topics, there's changes of C, but this difference equation still forgets the initial conditions, or the equivalent statement is start off at 2 different initial conditions and the trajectories will merge. So I've mentioned there's this de Groot-Friedkin model of the evolution of social power, and I've told you that you could get the development of autocracy, and we've considered the possibility of dynamic topologies, or changing the relative interaction with neighbours, and shown that you can get an exponential convergence. And there's a unique equilibrium if things are fixed, and a unique periodic trajectory when there's a periodic topology, like in government cabinet meetings. So the last thing I want to talk about is multiple and related opinions, where a group of individuals are not discussing topics sequentially, but are discussing multiple topics at the same time. And we see a quite different form of outcome here too. So we're interested in studying how you get disagreement, or even consensus can arise as a result of people discussing a set rather than a single topic, and as a result of the people, when they're discussing the set, having a private view about how the components in that set of topics are logically related. So I'll explain some of this in the slides to come. So it's often the case that our motivation or our opinion on one topic can depend on our opinion on another topic, because we build within our minds logical independencies. For example, everyone might agree that mentally challenging tasks can be as tough as physically challenging tasks. Or maybe not everybody would agree, but many people would. But they might not agree that Go or chess should be Olympic sports, but it's clear there's some kind of logical connection between the question, are mentally challenging tasks as tough as physically challenging tasks, and the question, should Go or chess be Olympic sports? So what does a multi-topic the group model look like? So here's a picture. If I had the CIs replaced by the identity matrix, then I would just have the group model. The YIs in the group model, the opinions of the ith individual, are scalars. When we have a bunch of topics, then the YIs for a single individual become vectors. There are here M topics, and so M entries of the vector YI. Now the CI is in there to capture this notion of logical dependence within individual I's mind, and I'll say a little bit more about that in a moment. So as I've just said, it's the logical matrix capturing the logical interdependencies between the topics for individual I, and we'll look at it separately. So let's consider these two possibilities again. Mentally challenging activities can be as tough as physically challenging activities, and Go and chess should be Olympic sports. So I'm going to introduce a matrix CI for the individual I that indicates their logical, the way they logically think about these two things. The entry CJK captures the logical dependence of topic J on topic K. And your opinion on topic 1 is, you can see that topic 2 is more a consequence of topic 1, and topic 1 is not really a consequence of topic 2. The logic flow goes one way. And the fact that the logic flow goes one way is what gives rise to a 0 here. And one-way logical dependence is common, and because the flow certainly does go in one direction, you'd expect, you would consider this in the light of your view on 1, there's a 0.5 comes in here. Now, picking the value of these numbers is in a sense anybody's guess, but the sign of the numbers and the presence or absence of zeros is something that's a bit more readily determinable. Now, if individual I had no neighbours, then according to that model I showed you before, this is the equation that the opinion vector of individual I would display. And so if individual I were to set off there with this particular CI, you'd end up with this particular steady state. And you can see that in order for that to happen, CI's got to have certain properties. So CI is the mechanism whereby the opinion of an individual in the light of the way they think about the world comes into some kind of coherent vector, or a vector that's coherent with their opinion of the world, and that's done via the matrix CI. CI represents individualized logical processing in order to secure a consistent belief system. And there are algebraic assumptions on the eigenvalues and the entries of CI which have to be fulfilled, but I'm not going to tell you what they are, I'll just assume they are fulfilled. And we'll also assume that the zeros occurring in CI are the same for every individual CI. The individual matrices CI aren't necessarily the same, but their zero pattern is the same for all the different individuals, because this is a matter really of logic and not just opinion. So that's the equation we're looking at. And it is common that the logic matrices are triangular when there's a logical one-way dependence between various topics, because you're building on some kind of fundamental axioms. So what happens, given these assumptions on CI that say our brains are working okay, given a connected graph, we do get exponentially fast convergence. And the questions of interest really are, what are the final opinion values? And particularly, are we going to get a consensus or not for one or more of the topics? Those are the questions of interest. Now, I might say, if all the C's are the same, that is, if all the individuals had the same view of the world stored in their brains, then you would reach a consensus, but that's a bit unlikely. So let's just think about there being two topics. So not P, but just, or P equals 2. And let's suppose there is a one-way axiomatic flow, so to speak. Then what you can say is that consensus always occurs for topic 1, and it sometimes occurs for topic 2. And it will occur for topic 2 if you don't have any individuals that have differing signs for this thing here. So the sign, as opposed to the value, is kind of how you roughly think about the world, roughly, because the value is not important, but you're saying that there's a positive dependence rather than a negative dependence, say, if this is positive. And if the CIs are all different, but they've all got the same sign pattern, then you will get consensus, even if the values are not the same. Disagreement in 2 occurs if and only if there's individuals that have differing logical views. Here is an example that in topic 1, everybody comes to the same opinion, and topic 2 being discussed at the same time, everybody comes to the same opinion. This is simulation stuff, of course, and all the entries have the same sign but different values. On the other hand, if we have a situation where all the C's are the same except for one of them, then we do not get consensus for the second topic. And in fact, even the people with C's of the same sign all split their views and we're all over the place. On the other hand, topic 1 does reach consensus. So what about 3 or more topics? It's quite complicated, and we have a paper where that's treated, and I'm not going to state a theorem or anything like that, but some high-level conclusions. You will only get disagreement if there's a cascade logic structure, that is, CI is block lower triangular. If all the CIs are full matrices, you won't get disagreement of opinions. And the disagreement can only occur if there's differences between 2 individuals, and you're more likely to have disagreement in a topic if it depends on many other topics, or if there's a disagreement in an earlier topic that a later topic depends on. So what I've done now is introduced a model for the discussion of logically interdependent topics, and I've established conditions on the network. We have established conditions on the network and the logic matrix for each individual that give us convergence of opinions to a steady state exponentially fast, and we can analyze and see which topics will reach a consensus and which fail to do so. And belief dynamic systems with cascade logic structures it can create disagreement, even without stubbornness. It's been a bit of a puzzle in the social network literature to state general conditions under which consensus is not reached. And this work shows that you will not reach, that there are circumstances in which you will not reach consensus, even if there are no stubborn individuals. There are circumstances in which you will not reach consensus because you're discussing multiple topics and the individuals have different views in their minds of how these topics are logically related. So I just want to finish by talking about some I call recent and future directions. There's a phenomenon called the spiral of silence, where people stop expressing opinions if they believe that others are moving away from their current opinion. So they see a derivative. They don't just see the instantaneous values, they see a derivative. It's kind of a sensing of the derivative and then incorporation of the derivative into the way they update their opinions. So we have not done that, but that would be something doable in the express and private opinion model. Another thing that we actually have written about is this. If an individual is successful in persuading other people to their point of view in a meeting, and if they're arrogant, they may lift their self-confidence even more than a conventional individual. Or if an individual is a humble individual and sees that they didn't have much effect on the outcome of a discussion, they may lower their self-confidence more than a normal individual. So these are two examples of behavioral characteristics where people's self-confidence changes not in what you might call a neutral way, but it overemphasizes something positive or something negative. Other individuals just maintain absolute uniformity, and others have a high if they do well and a low if they do badly. So you can capture those individual behaviors in the social power dynamics. And one of the conclusions is that you can get autocracy occurring even when you don't have a star network and the autocracy revolves around an arrogant individual. We also want to understand what belief system structures most naturally lead to strong diversity. That relates to the last topic. And here's something I haven't talked about: the mixture between opinions and actions. So someone takes an action, and as a result of that, there is a subsequent influence on the opinions that people have. So you need to model the co-evolution of actions and opinions. So that brings me to the end of my technical remarks. But Xiao Shui has asked me to say something about what I did with Purdue and maybe even give some advice to graduate students and postdocs. So I do have 2 slides, and I think it's probably appropriate to go on with them now. Xiao Shui will cut me off if it's not appropriate.
No, Brian, please go ahead. Yeah, definitely. We need your advice, especially our young researchers, and for your research and also study.
Right. So I've visited many universities in my life, and I think my first visit to Purdue was more than 50 years ago. It was probably to electrical engineering, but of course I met a number of engineering people interested in control, and I really remember little about it. And then about 25 years ago, I was a guest of Professor Robert Skelton, who I guess was in aeronautics and astronautics at that time, although I'm not sure. He subsequently moved to the University of California. But in recent years, I've been the guest of Professor Mo, and I want to say he's a great host, and I'm looking forward to my next visit. I'm sorry I couldn't give this talk in person. And I should say, as a result of these visits, we've produced several papers. The interactions did involve graduate students, and I think we all enjoyed ourselves. We were not just doing our day jobs, but we were having fun. And I developed a general sense of warmth towards Purdue and a strong feeling of friendship with Professor Mo and indeed his colleagues. And I also am quite sure that face-to-face interactions work much better than computer screens and email and that sort of thing. So I certainly would hate it if we could never visit one another again. So that's what I've done with Purdue. And now I was asked to give advice for graduate students and postdocs. And I've picked 3 pieces of advice, and I'm also going to expand on each of them a little bit. The first is to become a good communicator, because then people will take more notice of you, which is probably what most people want. And there are different ways in which you need to communicate, and they need different skills. One is technical writing, that is writing papers for journals or conferences. The skills for that are quite different to the skills for giving a seminar, and the skills for those first 2 are quite different to the skills for writing a proposal, a research proposal. And then if you're interacting with people, you do need to be able to engage in an informal discussion at the blackboard, which involves a clear and efficient transmission of information. And you often don't have notes that are prepared for that. It's an evolving thing. So that's quite hard. And then you may find yourself in the elevator with the president of the university or the secretary for education in the state or something like that. And they say, well, what are you doing your thesis on? And you've got 30 seconds to explain in non-technical language, but to interest the person in what you're doing. And that's what I call an elevator speech. Or you're applying for a vacation job, and you're given a minute with the overall manager. And he says, what's your thesis about? And in 30 seconds, you've got to say what your thesis is about to a person who's technical, but you don't know if they know anything about control. That's an elevator speech. So the second thing that I wanted to mention was that travel and generate a network and widen your horizons. You do need to go to conferences, and as a result of going to conferences, you don't just absorb information, you meet people and you form links, and they become part of your network. It's good also if you can make laboratory visits. I imagine Professor Mo has on his resume the fact that when he was a graduate student, he spent some time at the Australian National University, and I'm sure he would say that helped him widen his horizons, and he valued that experience. And in doing this, you can meet professors from outside your own institution from whom you can learn. And if you have an extended enough interaction with them, they might even be able to write you a good reference. So traveling and generating a network and widening your horizons is very difficult. It's very important. And then the third thing is to set yourself high standards. You must show integrity in dealing with people. It's as simple as that. And then there are these aspects of personality merging into character, like being on time for a meeting with someone, being reliable. That is, if you say, well, you'll have the document from me next Wednesday, it should be available on Wednesday. Working hard, not losing stuff, and organising your life so that you have the right balance of work and leisure and the right amount of exercise and sleep and appropriate eating. Because if you don't maintain high standards for yourself in terms of the way you look after your body and the relationships with other people, you're going to find it harder to do good work and to collaborate with other people. So that's my 3 pieces of advice. And perhaps here I should stop sharing, shall Shui?
Sure. Thank you very much, Brian. Both the technical talk and also the your experience at Purdue. We definitely look forward to host you again. Your visit to Purdue in person again in future. And also thank you for the advice. I do enjoy it a lot in visiting you and NU. Not just the the research we have done, and also through that opportunity, I also have known many other researchers like Wei Helmke, and also Wei Zhen. Actually, Wu Wei wrote me a recommending letter for my job hunting at Purdue. And and also you mentioned the communication. Yeah, that's definitely, I would say we need to emphasize more on training our students. Sometimes we focus more on the research part, how to identify a research problem and solve it. But for example, for the communication presentation, I believe we also need to emphasize more. Thank you very much, Brian. And we look forward to your next visit, definitely. So next, I believe more like our Q&A. So for all students and all the attendees, please type your questions in the chat window. And I do have the first question from Professor Dengfeng Sun. And he asked about any comments on modeling individual behaviors.
Well, I'm not sure I know what's fully behind the question, but let me say this. Modeling in social networks is there's nothing like modeling in electromechanical systems. In electromechanical systems, the physics underlying the models is known, and the parameters in the models are typically pressure or mass or flux or friction or something like that. And the understanding of what that parameter is and the measurement of it would be the same in Australia and China and the United States and France. And the equations are the same. On the other hand, if I say that I have an opinion value of 0.7 sitting here in Australia, someone in the United States might say, well, what's your scheme for measuring? Because there is no standardized way of measuring opinion values. And an opinion value of 0.7 for me, when I say it, is kind of a subjective statement rather than one that depends on international standards of weights and measures and so on. So in the course of the talk, I emphasized that linearity in some of these equations was a heroic assumption that is not grounded in physics. Likewise, the statement that we can talk about self-confidence and levels of opinions lying in an interval -1 to 1 or 0 to 1 is also kind of a heroic assumption, because repeatability and consistency of language across researchers and across countries is not there either. So all that is an enormous beware to the user warning of these theories. But to the extent that the theories do capture field data and laboratory data, the field data can involve hundreds of people in the alcohol consumption experiment. There is some validity. There has to be some validity in these models, but you just shouldn't rely on them too much, I guess. I don't know if that answered the question.
He said yes, thanks.
I'll add one thing. Sorry, I know there's another question, but there have been laboratory experiments, especially run by Friedkin, for the models with which his name is associated, and they've been laboratory level experiments, and they would be regarded as validating the models. Yeah. So another question.
Another question is actually for me, but you should skip it if there are other people asking a question.
So the question is, in the presence of disagreement, any comments on ways of control to gradually shape the network to reach consensus? So this is a super question. Another way you could ask the question is, what are good strategies for a chairperson to use? Because generally speaking, the chairperson of a meeting should be striving, I mean, normally, not always, to get the meeting to come to a consensus and people leave the room happy and committed to doing whatever it is decided. And I'm not sure that I could say much about that. I think the models the models are maybe suggestive of where one might start to do something. Appreciating that things like a Perron-Frobenius eigenvalue can play a role is important. Maybe the notion that there are important and less important individuals in a meeting is quite important, and probably people who chair meetings that generally produce consensuses are aware of a whole lot of things which it is useful to do to help produce a consensus. But none of these things, as far as I'm aware, has been the subject of modelling in the sense that I've been talking about the models today. And I'd like to think that the models might even suggest something else that people could try, but that's a very speculative remark.
Thank you, Brian. Actually, I asked that question basically, more, for example, if you look at social network, if the network has the links and also have the nodes, which are individual persons. For example, for the, and disagreement is, I believe, is the frequent case. And we cannot add arbitrary control to the node or to the link. Right? We have some constraints for the control. So more like from the control perspective, I believe more like it might be valuable to give some recommendations for them where and how we could enter somehow some way of control to shape the society's consensus. So
let me give you a couple of ideas. In connection with the notion of a government cabinet that discusses a standard set of agenda items every cabinet, like every week or every fortnight or something, and defence and health and social security, there may be some optimum orderings of agenda items. And if you're the chairman of a meeting, and that's one idea, and we recorded that idea, I think, in a paper as an idea for the future. Again, if you're the chairman of a meeting and you see that a certain individual in the meeting makes very intelligent, balanced, clear remarks, you do, as chair, have the opportunity to call on that individual more frequently and say, look, is there anything you'd like to add to that? Or we were talking before the meeting and it seemed to me you had an interesting view. Could you tell your colleagues? Something like that, where you get a greater injection of opinion from a valuable individual than from a less valuable individual. You're not stopping other people talking, but you're just making sure that this person's opinions are well and truly injected into the meeting. That might be a way by which the network could be moved closer. In fact, I'm sure it is. The network is moved closer to consensus.
Thank you, Brian. Thank you.
Yeah.
And so, Shreyas, should we move to the meeting with ICON faculty, or?
There's one more question, I think, in the chat that I think is a very important and good one. So this is from Samyut Trickler. She's asking, how are factors like age, gender, and other relevant aspects of identity incorporated when analyzing social power? Could you incorporate those in the update equations?
Yes, that's a very good question. And in fact, I referred to some field data concerning alcohol consumption at Princeton University. And this was in conjunction with expressed opinions and private opinions. And the fact that there was this substantial study lying around, and you could put it in the framework of the model I discussed. So in that putting it in the framework of that model, based on the field data, the women were grouped separately to the men. And it's not a surprise that among freshman undergraduates or undergraduates generally, men have different attitudes to alcohol than women. And the fact that they were freshmen rather than sophomores, I think was also part of the thing. So there were different populations, if you like, that were, of course, all interacting. And so what was done in our modelling was to assign different values of stubbornness and resilience parameters to the women group and the men group, roughly speaking. We may have done it also with freshmen and sophomores. I can't remember now. And so that was very revealing. And in fact, that was very important in order to get the model to churn out stuff that was consistent with the field data. And this was good also because it showed true dynamic effects. So in evolution, as people got more experience in being on campus. And so it wasn't just getting older, it was actually expressing and re-expressing of opinions. Certainly the answer is aspects of age, gender, and other identity aspects are relevant. And I see there's another question. Should I answer this further question?
Certainly. I think we'll keep this as the last question. But yeah, so I'll just read it out loud for everybody. Are there models available to study the effect of adversarial individuals who are trying to produce a disagreement?
I think they're of contemporary interest. Let me say that the ASH study, where there were, if you like, 7 adversary individuals out of the 8. So in a sense, they're not an adversary, but you know, they were behaving like adversary individuals. And in our studies, we've also dealing with this model that we came up with. We've also postulated that there were many adversarial bots and considered the nature of the network connections to the bots and their, I mean adversarial bots, and their ability to influence or not influence the network very much, and the issue of whether the network was highly connected or loosely connected, or things like that. We've also done that, but I can't remember how much of that we actually reported in the paper, and I don't know that there's this many papers available yet. And I think it's a very important question. And the elections in the US in 2016, and then later 2020, where foreign governments appear to have tried to influence public opinion. It's a matter that's taken extraordinarily seriously in this country. I've actually had discussions with a gentleman who's called the Australian Electoral Commissioner, whose legal position is concerned with maintaining integrity of the whole process. And believe you me, they're very focused on stopping this sort of nonsense.
Wonderful. Well, thank you, Brian. I think that was a wonderful seminar and a wonderful discussion. So on behalf of everybody, we'd like to thank you. If you were here, you'd hear the applause from everybody. You'll have to trust us.